Good morning, students. So this is our last section on our first part of the year, which was dedicated to multivariate calculus. So what we're going to do is called line integral. Some other names that you may find are curvilinear integral or curve integrals. Okay, so as you see, it's really the last pages of the lecture notes, and that's not very long, but it's really some new concepts, I believe. So we're going to spend, I think, one or two, rather two sessions of lessons about that. Okay, so let me open a new page. Okay, so here it is, and let's try to introduce this topic. Okay, so let's say you have a force in the plane. Let's denote it with an F, a force vector depending on x, y, and it's going to be applied along a displacement. Let's call that displacement AB, a path AB. And you know how to calculate the work of this force on a displacement AB. It's just going to be given by the scalar product, the dot product of the two vectors. Okay, so it's magnitude of F times magnitude of AB times the cosine of between the two vectors, or any other ways you can calculate the dot product between those two. What's happening now if instead of just AB, we want to compute the work of a force on a displacement that is going to look like a curve. Okay, what about something like this, right? That's so the first idea is that we are going to approximate the work on this curve, right, by saying we are going to approximate this curve by broken lines. So that would be we would take some, let's say that's A0, A1, A2, etc. And we're going to say, well, I'm going to approximate that curve by straight lines, and okay, and then I can compute the work on each of these straight lines. So the work now would be given by, well, we would have for one of the segments, we would have the force at, let's say, point AJ, okay, times the vector AJ plus 1, okay, and I should sum that for I is equal to 0 to, well, according to my notations, n minus 1. Okay, and so that would give you an approximation of the work of this force along that curve. And as usual with integrals, what we're going to do is to say that our subdivision is going to be smaller and smaller, and as that size, let's say that this has constant size, usually we call that h, it becomes infinitesimal. That's the sense of the infinitesimal term in the integral. The limit of this thing is going to, as that size tends to 0, is going to define something that we're going to call the line integral. Okay, so that limit as h tends to 0, that's going to be something, for the moment, we're just going to say that's a notation of f times displacement a, infinitesimal displacement a, and I'm going usually to use that letter, so the capital gamma, to denote the curve. That's a very usual letter to denote a curve, okay? And so we will say that the work of the force along that curve is going to be given by the limit as the subdivision, the size of the subdivision tends to 0 of this sum, and the notation we're going to use is going to be that notation. Okay, so this is the notation we're going to use. All right. Okay, so let's give a few more insights about this computation. So let me rewrite that sum. So I've got the sum from 0 to n of f hij times vector hij plus 1. Exceptionally, I'm writing the arrays, but that's going to be over very soon. So let's assume that your force F has components as components. Okay, let's say that we should give some names to this thing. Let's say that F has components. Let's call this A, for instance, and B. Okay, and let's say that this vector is going to have well, any points aj is going to have components xj, yj, so that this vector is going to have components xj plus 1 minus xj and yj plus 1 minus yj. Okay, and the force, so that the AB are actually depending on, well, that's going to be A of xj, yj, and B of xj, yj. Okay, the components of my force vector are going to depend on the location in the plane I'm looking at. Okay, so let's go on our calculation. Well, let's make a bit more explicit our calculation, right? So you know that the dot product, when I have the Cartesian coordinates, I can rewrite this as, well, the product of the x components plus the product of the y components. So that's going to be axj yj times xj plus 1 minus xj, all right? That's x component of f times the x component of my displacement vector, plus the same thing in the y component, so plus b xj yj times yj plus 1 minus yj. Okay, all right, and so the idea is that we're going to see actually a new notation. The notation we're going to use, as this tends to 0, well, that the size that I called h, the difference between aj plus 1 and aj, the distance between those 2 points tends to 0. These two displacements in x and in y are going to tend to infinitesimal values, and we already have a notation for that. The limit as it tends to 0 is going to be called dx, and that is going to be called dy. So that the notation that I used here, like integral on the curve of f times this infinitesimal displacement vector, we will be able to rewrite it as, so the integral will still have, we're still going to say that's the curve of axy times dx plus bxy times dy. Okay, so actually I've got several ways to denote the line integral that I'm talking about. So the first way we said was, I'm just taking my so f dot product with my displacement vector, and actually this notation, the second one, is the one that we're going to use in general. Okay, so for the moment you can think about this just as a notation for this idea that we have introduced. Now let's go a bit further. You see that I've just said I'm integrating on gamma, and the same way as when you were doing multiple integrals, it was the most important, well, one of the most important thing in order to compute a multiple integral was to be able to describe precisely the domain you wanted to integrate on. Okay, so the same way we will have to work a lot to be able to describe precisely the curve we are working on. But it's great because last year you saw some ways to describe nice curves, and that was called the parametric curves. So what do we get? A parametric curve is just that we are going to describe gamma by saying it's going to be all the points described by x of t, y of t, for t between some values, let's say between 0 and capital T. Okay, and so your curve is entirely described by the set of all the points x, y that are described by, that are given by functions x of t, y of t. Okay, so that x, if I use again my, let me work again on the previous equality that we obtained. So this is, okay, so that led to write this as dx and dy. So what does this kind of term becomes now that you know that x depends on t and y depends on t? So let's write that. That means that actually when we write, oh sorry, not with, so big. When we write something like xj, it corresponds actually to x at some time tj, okay? So it's, if I've got my curve given like that, and that was my point A0, that corresponds to T0, first T1, T2, etc., and up to endpoint would be given by Tn. All right, so xj is actually x of tj, and yj is y of tj, of course. So when I've got things like x j plus 1 minus xj, that's actually going to be given by x of tj plus 1 minus x of tj. But, well, now you know that you can get a very good approximation of this thing as a function of t. That's, if you want a first order approximation, that's going to be x prime of tj times the difference tj plus 1 minus tj. And similarly, you've got, if you want to express the infinitesimal displacement in the y direction, you get yj plus 1 minus yj, which would actually correspond to y of tj plus 1 minus y of tj. That would be given, that would be could be approximated by y prime of tj times tj plus 1 minus tj. So that in my previous equality here, the terms that I've been outlined in orange and that would give you the dx dy, they can both be expressed as depending here, so these two terms, they can both be expressed as depending on tj plus 1 minus tj. And so the idea is that when my interval between 2 points, okay, between 2 points becomes infinitesimally small, that means that this thing here, they tend to some infinitesimal displacement, but in the same variable, dt. Okay, so now what do we have? We can rewrite this line integral as being, so we had the second expression notation that we had obtained was this one, b of xy times dy, which was expressing the dot product between the force with components AB and the displacement with components dx dy. You can actually now describe it as you're going to have ax of t, y of t times x prime of t times dt, but then I can factor the dt in the end, be x of t, y of t times y prime of t, and the two of them are going to be a factor of dt. And the good thing is that now I can give some precise bounds to my integral. So it's just going to be between, first point is going to be between t0 and the last point is at capital T. Okay, so that describes my whole curve. So, and here it's still a notation if you like, but this is really an integral of the kind, an integral that you know how to calculate. Okay, good.